Welcome to this explainer. You know, when you look at a plant or a traditional medicine, you're actually looking at a highly advanced microscopic biochemical factory. And today, we aren't just talking about surface level benefits. We are zooming all the way in to the atomic level. We're going to map the exact chemical architecture of Ocimum sanctum, which you probably know as holy basil or Tulsi. We'll decode its most fascinating molecules, break down their structures, and reveal exactly how they interact with human cellular receptors. Now, revered in Ayurveda as the elixir of life, this plant has literally been utilized for centuries to promote longevity and help the body adapt to stress. But what is truly fascinating to us today is how modern science is stepping in to validate these ancient claims. We are moving right past the folklore and diving directly into the pharmacology, looking at exactly why this plant is such a powerhouse.
So how do we know all this? Well, through advanced analytical tools like gas chromatography mass spectrometry and HPLC. Think of these as high-tech molecular sieves. Researchers have used them to completely decode its chemistry. And they've revealed a highly complex phytochemical arsenal consisting of dozens of bioactive markers that work both individually and synergistically. Here is our roadmap for today. 1. Propanol phenols. 2. Terpenoids. 3. Flavonoids and phenolics. 4. Fixed oils and lipids. And finally, number 5. The clinical convergence. Let's get right into it. Section 1. Propanol phenols.
What's really interesting here is our first hero molecule, eugenol. Chemically, it's 1-hydroxy-2-moxy-4-allyl-benzene. Yeah, quite a mouthful. But this is the predominant component of the plant's essential oil, and it acts as a primary antifungal, antibacterial, and even an anti-cancer agent. Its unique structural features allow it to easily penetrate microbial membranes, which makes it a highly effective first line of defense. And this next point brilliantly illustrates the sheer precision of these phytochemicals. Eugenol is highly effective against gram-positive Staphylococcus aureus, but, and this is wild, if you add just a single methyl group to create methyl eugenol, the targeting shifts completely. Methyl eugenol exhibits significant activity against the gram-negative bacteria Pseudomonas aeruginosa. Tiny molecular variations literally dictate entirely different bacterial targets. Notice the pharmacology of how eugenol destroys drug-resistant Candida strains. The mechanism is completely systematic. First, laboratory assays using propydium iodide show rapid penetration into yeast cells, proving that eugenol causes extensive lesions in the plasma membrane. It physically disrupts the membrane's integrity. And then finally, it causes a massive reduction in the biosynthesis of ergosterol, which is a sterol entirely specific to fungal survival. So it doesn't just inhibit the fungus, it dismantles its entire structural foundation. Section 2. Terpenoids. Let me introduce you to ursolic acid. Structurally, we're looking at a potent pentacyclic triterpenoid, essentially a massive 5-ringed molecular structure. This is a major marker compound for the plant, and it acts as a true anti-inflammatory powerhouse. But, you know, like a lot of complex phytochemicals, delivering it effectively into the human body has historically been a real challenge because of bioavailability issues. So the crucial takeaway here is this massive number, 89.56%. That is the entrapment efficacy researchers achieved when they loaded ursolic acid-rich extracts into nanostructured lipid carriers, or NLCs, specifically for transdermal delivery. By engineering these tiny 120 nanometer spherical particles, scientists were able to create a prolonged 12-hour release of the drug straight through the skin. Clinically, studies show these specific ursolic acid nanocarriers ameliorate adjuvant-induced arthritis by directly shutting down exact inflammatory pathways. We're talking about inhibiting COX-1 and COX-2 enzymes and drastically reducing the pro-inflammatory cytokines TNF-alpha and interleukin-1. It's essentially silencing the body's chemical alarm bells for pain and swelling. In fact, its anti-arthritic activity actually performs right on par with standard marketed synthetic diclofenac gels. Okay, moving to Section 3, flavonoids and phenolics. This data perfectly synthesizes how specific flavonoids address chronic, stubborn issues like diabetic foot ulcers. In poorly managed diabetes, elevated levels of an enzyme called MMP9 severely slow down wound healing. But through molecular docking and dynamic simulations, researchers found that phytochemicals like apigenin, luteolin, rosmarinic acid, and quercetin aggressively bind to MMP9 with incredible affinity, ranging from -9.1 to -9.8 kilocalories per mole. And in molecular docking, the lower that negative number goes, the tighter and more aggressively the molecule locks onto its target.
They actually outperformed synthetic inhibitor alternatives, which accelerates the healing process naturally. And this maps out the exact cascade where the plant's ethanol extract blocks metastasis in NCIH460 non-small cell lung cancer. It targets osteopontin-mediated metastasis by first inhibiting the PI3K/AKT signaling pathway. That leads directly to the suppression of COX-2 expression, which ultimately reduces vascular endothelial growth factor production and MMP9 activity. It essentially cuts off the communication and supply lines that cancer cells use to spread and invade new tissues. It's brilliant.
Section 4. Fixed oils and lipids. Meet alpha-linolenic acid, an omega-3 fatty acid that is highly concentrated in the plant's seeds. What makes this fixed oil component so incredibly special is its dual-pathway anti-inflammatory effect. It possesses the rare capacity to block both the cyclooxygenase and the lipooxygenase pathways of arachidonate metabolism. Finding this kind of dual inhibition in a single natural entity is pretty unique, and it perfectly explains its potent pain-relieving and anti-swelling properties. When tested in models fed high-fat and high-cholesterol diets, this fixed oil acts as a powerful anti-hyperlipidemic and cardioprotective agent. Notice how it actively decreases total cholesterol, reduces triglycerides and LDL, and lowers the overall atherogenic index. It achieves all of this primarily by suppressing liver lipid synthesis right at the genetic level, effectively protecting the cardiovascular system from the oxidative stress and damage caused by hyperlipidemia. And finally, Section 5, the clinical convergence. This is where modern chemistry is now utilizing the plant's extract itself as a natural reducing and capping agent to synthesize highly reactive, eco-friendly therapeutic nanoparticles. Instead of using toxic industrial chemicals, the polyphenols and flavonoids in Ocimum sanctum facilitate the creation of biogenic silver, titanium dioxide, zinc oxide, and even palladium-doped copper oxide nanoparticles. It's green chemistry at its finest. Just look at the incredible anti-biofilm activity of these green-synthesized silver nanoparticles. When tested against severe, multi-drug-resistant bacteria isolated from clinical cases, these nanoparticles dismantled biofilms at a staggering rate. We're talking about inhibiting MDR E. coli by over 80%, Staph aureus by over 71%, and Klebsiella pneumoniae by over 60%. And why this matters is exactly how they are doing it. These green synthesized nanoparticles literally shut down the genetic efflux pumps, specifically genes like AKRB, AKRE, and NORB. Now, these efflux pumps are the exact mechanisms that multi-drug-resistant bacteria use to spit antibiotics right back out of their cells. By downregulating these genes, the nanoparticles strip the bacteria of their primary defense mechanism, opening the door to overcome antibiotic resistance entirely. So, as we conclude this explainer, we really have to ask, how will the pharmaceutical industry scale this? We've clearly seen that Ocimum sanctum is not just some traditional herb, it is a microscopic biochemical factory. It contains eugenol to rupture fungi, ursolic acid to silence inflammation, flavonoids to halt cancer metastases, and the exact reductive capacity to synthesize next-generation nanomedicines. The molecular blueprint is fully decoded. The question now is how quickly modern medicine will harness these precise chemical architectures to redefine targeted, eco-friendly drug development. Thank you for joining me, and as always, keep exploring the science.